Now I'll come to the next big fuel, which is diesel. Diesel has now become suddenly a bad word. Hey, people are talking about we'll phase out diesel. But people should remember also that the fuel efficiency of a diesel vehicle is higher than that of a petrol vehicle. So the amount of carbon dioxide that you generate per mile that you travel will be less for diesel. But diesel was always considered to be a bad boy because of the presence of things like sulfur. It would emit sulfur oxide emissions. So these were the things why diesel fell a bit out of favor. But let me tell you, even today, all our trucks, everything, they all run on diesel. So who was the man? It was Diesel, Rudolf Diesel. He is the one who invented the diesel engine. And as you know, over here, by the process of compression, I reached the very high temperatures through which the ignition is done. I was extremely fortunate because we were working with Mercedes, and I'll tell you about that. They made me sit in the first car that Diesel made. This is in Stuttgart, where the Daimler-Benz head office is. What he said was extremely prophetic. The diesel engine can be fed with vegetable oils and would help considerably in the development of agriculture of the countries which use it. He was actually looking at agriculture. And the tragedy is that in our country, we are even importing a large amount of edible oil. We don't even have enough of crops to make our own edible oil. So in our country, using it for converting edible oil, for example, into diesel, would not make much of a sense. But then you have to look at alternative strategies, and you get into exactly the same kinds of dilemma which you would have seen when we talked about using sugarcane juice to make ethanol. Because if you want to do that, you'll have to divert some of your food crops into making fuel. And you have to ask yourself whether it is a wise thing to do or not. Now, biodiesel, just like, for example, ethanol, all of this would be equally true. What it does is that it helps you to reach a neutral carbon balance, because the carbon dioxide which I'm emitting when I'm burning my fuel, that is actually getting mopped up by my plants. So I have a net zero in terms of how much CO2 I'm emitting and how much I'm fixing. Because in photosynthesis, you have to fix carbon dioxide. So that's your carbon capture and carbon release. So when today people are talking about net zero as the target by 2050 for climate change, to restrict the rise in the temperature to within 2 degrees centigrade, that's what you're talking about. You're really talking about having those kinds of situations where either you cannot be carbon positive, but you can try and be at least carbon neutral. So that's the reason for the interest. Diesel, of course, was not interested in all that. Initially, Diesel's interest was at that time in 1911. These refineries came later. At that time, he could only run it with vegetable oil, his engine. But the thing is that today, you cannot run your engines with just a pure vegetable oil. What diesel could do. Like over here, in this vehicle, it won't run. This will run, but if I try to run a present day Mercedes with it, won't. Okay, the reason is because earlier the engines were all low speed engines. Today, you have got very high speed engines. And what it means is that the nozzles through which the fuel has to be injected are extremely fine. And your natural vegetable oils are much more viscous than diesel. And so it becomes very difficult to pump that oil, to make a spray of it at that kind of a dimension which you require in a high-speed engine. That's the biggest problem. And that is the birth of the so-called biodiesel. So what is biodiesel? This was recognized quite some time back by this person called Walton. He said that this is the problem. So what he said is, what is a vegetable oil? A vegetable oil is basically a triglyceride. or even an animal fat, a lard. These are all triglycerides. What are triglycerides? There is a glycerol, and there are three OH groups sticking out from the glycerol, and each of them I've got basically a hydrocarbon chain which is fixed to it in the form of an ester. So it's a triglyceride. That's what it is. So what he did was that he conceived the idea and he said, look, if I look at the individual chain lengths in the triglyceride, they are quite comparable to the chain length of diesel. So what he said, without doing a single experiment, is that if I can break apart the oil just to hydrolyze it, what will happen is I'll get a fatty acid, and then I'll get my glycerol, and I'll get a long chain fatty acid, and I'll take out the glycerol and see if I can run the engine from the residual fatty acid. And that's the birth of the biodiesel, what people today know. Much later, in 1937, the Belgians took the first patent where they were able to take something like palm oil, and then they split apart the triglyceride and ended up with a chain length which was quite comparable to that of fossil diesel. And they actually ran a vehicle in those days, 1938, from Brussels to Leuven. So this is the first actual work that was done with biodiesel. Most of the time, I think even these people probably did not use 100% pure biodiesel. They may have taken 10%, 15% of biodiesel, mixed it with about 80-85% of fossil diesel, and ran the vehicle. And then, of course, the action shifted to South Africa. These people then actually developed the first pilot plant. And then later on, the Austrians acquired the technology from South Africa and put up the first 30,000 ton biodiesel plant based on rapeseed. Rapeseed is what grows in Europe. So their plants were based on rapeseed. And this plant is 1989. So fairly recent development, biodiesel. Now, in 2004, we had a very successful collaboration with Mercedes-Benz. So that's why I put India and Germany jointly. For the first time, were able to run a vehicle with neat biodiesel, means 100% of the product that you obtain from the vegetable oil. There's not a gram of diesel anywhere. Much later, 2009, the first aeroplane was run by Air New Zealand, a Boeing 747. I think it had about 50% of the biodiesel and 50% was kerosene. But this fuel is very different from this fuel. So I'll talk to you about this also, what exactly this is. So the two fuels are different. So what was the result of this? You see, in 2004, for the first time, and this is the first such study done in the world, where you can see Mercedes to run on pure biodiesel, 100% biodiesel, and two such cars ran, one in the northern part of India and one in the southern part of India, covering about 6,000 kilometers each. This is what really made India very famous because of this work. Now, this is quite a interesting process. Take, for example, the case of Jatropha, which is one of the plants which was very much talked about as a possible feedstock for biodiesel. And this is how the fruits look in the tree. These are the fruits, and then one deshells the fruits. So you'll get the empty shells collecting here, and then you'll get the seeds. Okay, so there's a machine that does this. The shells also have very good calorific value, so you can do a pyrolysis of the shells, and you can actually generate electricity because it produces a gas which you can put in your engine and generate power. So this power is being generated from these shells, or you could basically get process heat as you require it. Then these seeds are crushed. This is an oil expeller. So they contain about 35% of oil. So you crush it in this expeller, and that's how you recover the oil. And the cake that you get, the oil cake, you can actually plow it back into the field because it's a very good manure. You can use it. It's very rich in all the nutrients. So that way nothing goes waste when you're doing this. And then comes the actual process of making biodiesel from the oil. You've got your oil. What happens is that when you do the analysis of the oil, what one finds is that any oil will have, of course, mostly the triglyceride oil, but there will always be some free fatty acids which are present, and those free fatty acids can be detrimental to the operation of the vehicle. So those have got to be removed, the free fatty acids. Now that is done by doing a very controlled neutralization of the acid, so that you're just forming the soap cake, because alkali can also lead to the saponification of oil. If that happens, then it's of no use. So you have to do it at a very controlled temperature, maybe around 55 degrees centigrade, and also use the right amount of sodium hydroxide, which will be good for just the neutralization of free fatty acid, and will leave your oil, the triglyceride part, untouched. Now, once you form the soap cake, of course, is a solid, so you can centrifuge it out from the oil. So now you have got oil, but that oil will have some amount of moisture, because this neutralization, actually you're taking a sodium hydroxide solution, and moisture is quite detrimental to the process of doing transesterification. And so one needs to basically, that step is not shown, but you need to, if the moisture level is beyond a point, then you need to drive out the moisture from the oil. Then what one does is that the process of transesterification is effectively, one takes an alkali and methanol. You could also do it under acidic conditions, the transesterification. Both are possible, but the more prevalent one is with alkali and methanol. So you've got your oil, you've got your methanol and alkali. So it does the transesterification, and the glycerol will pop out, and you have now a methyl ester from the transesterification process. If you are not very sure that a single stage transesterification has transesterified completely, then you might want to do a second stage transesterification. Usually it's not required if you do the first stage well. And then what happens is that by this point, almost all of the oil has got converted into methyl ester, which is your biodiesel. And what happens is that the glycerol, which is a byproduct, is not soluble in the biodiesel. So that comes out. You always have to take a surplus of methanol, a twofold excess over the stoichiometric requirement around that. And so some of that methanol obviously is very soluble in glycerol. That will come out, plus some of your catalyst will also come out. And so you'll get this as a separate phase, and you can decant your biodiesel. But the problem is that all of the impurities do not come out. There will always be a small amount which will be left behind in your biodiesel, which is formed. So basically what you have to do is that, suppose you have done 2 stages of this transesterification. Now you have got your biodiesel, and you need to get rid of all the other impurities. How would you think of removing all the impurities like glycerol, excess methanol, catalyst, potassium hydroxide? What would be the best way of taking it out?
So dissolving it in a polar protic solvent, because they all are dissolvable in that. Yes, sir. Dissolving them in water.
Dissolving them in
And
water,
so,
right? Huh?
and
Yeah,
so,
it seems like quite a logical thing to do, dissolve it in water. But what happens is that there will always be, in addition to your methyl ester, you will always have some amount of saponification which can happen. And especially if you put in water, if there is some traces of oil and you've got water and now you've got KOH, there'll always be a vulnerability to saponification. Now, once you have got a saponification, then what will happen is that I've got my, it's like a surfactant that I've created, a soap. I've got water, I've got oil, and you have got the perfect recipe for a very fine, stiff emulsion. Once you form the emulsion, then it becomes extremely difficult to separate the aqueous phase from the biodiesel phase. In fact, sometimes even if you leave it standing for a few days, it won't come out cleanly. There will always be some mixing of the phases. So that emulsion is extremely difficult to break. This is where most people had got stuck. I mean, you could make biodiesel, but invariably, the quality of the biodiesel was very poor. And as you have seen, that these vehicles were run on 100% biodiesel, and that biodiesel looks like this. It's absolutely clear. It's a very pure biodiesel. So what one had to do was find another solvent which is not water, because water was leading to emulsification. Now, it was also found that while studying the byproducts which come out, which come out of the biodiesel, that glycerol is of course being formed in the reaction, and it has a very strong affinity for all of these unwanted things. Plus, let me tell you, you could also form some monoglycerides and diglycerides. May not completely split off all the glycerol. One chain could be still hanging from the glycerol, or it could be two. So those are also there, and those were also, have a high affinity. But the problem is there's only a limited amount of glycerol which you get during the process of transesterification. By weight, it will be about 10%. That was found to be not sufficient to pull out all the impurities. So what was done was that instead of adding water to the crude biodiesel, one added glycerol. And this glycerol is actually recovered from this byproduct glycerol. Okay, you can treat it and get pure glycerol. So that glycerol is being put into the biodiesel. Now you've got sufficient glycerol to completely pull out all of those impurities which are lurking in the biodiesel. Now, once these things are all removed, now you can wash with some amount of water and get rid of traces of any methanol, etc., which might be present. But the beauty is that when you first treat with glycerol and then with water, no emulsion forms at this point. So, so that is the technology by which the world's best biodiesel was made, which can run any vehicle you can operate with the neat biodiesel. But there is still a problem that since you're adding water, and biodiesel has some amount of affinity for moisture. And if you have got moisture in your biodiesel, it can go and corrode the engine. So what you have to do is that you have to remove all of the water. Now, all of these steps are all room temperature operations. There's no heating involved. The traces of moisture, one could have, of course, maybe applied heat and pulled a vacuum and removed the moisture. But then, it would have been a bit silly that all of this is done at room temperature, and just for this last stage of moisture removal that you have to apply heat. So it was necessary to think of an alternative way of removing that moisture. And the best solution is that you can just sparge with dry air. And because dry air can absorb a lot of moisture, its saturation humidity level is much higher than what you'll have in dry air. And so what you do is that when you pass dry air, purge it, the outgoing air takes up the moisture from the biodiesel, and it brings it down to a acceptable level as per the specifications. And then the last thing is that sometimes what happens is that there can always be some amount of oxidation which can happen in these fuels because of the presence of oxygen. So you may also add an antioxidant, and that antioxidant is really added in a protective way, maybe at about 10 to 15 ppm concentration, very less. Oh, sorry, I mixed it up. You see, once you add the antioxidant after washing with water, and now when you sparge with dry air, even though there's a lot of oxygen, because of the presence of the antioxidant, there will be no oxidation of the biodiesel. Only the water vapors will come out along with your air. Okay? And then finally, you have got the desired biodiesel. I'll send you this patent for those who are interested. You can read it and you can follow the steps starting from the oil. The overall process of transesterification you can use in a much more broad manner. It's not just confined to oils which you derive from plants. Or it could even be that, like, let's say, some work which was being done with, let's say, Pepsi, because they make all these Frito-Lay chips and things like that. So they actually generate quite a bit of oil, which is the fried oil. And you don't want to keep frying your chips and all in fried oil because the oil starts getting rancid. So at some point you need to actually use fresh oil, and then that becomes a waste oil. Of course, that oil is not really a waste oil. People actually use it for making soap. But if you want, you could also convert that fried oil into biodiesel. In fact, this biodiesel which is being poured into this tractor was basically made using the fried oil which was provided by Pepsi. And sometimes what will happen is in technology, there can be a long gap between the time when you have actually invented a process, I mean, a very good process, and by the time that it actually gets implemented. Even in the Haber process, Haber invented the ammonia synthesis in around 1908, but it took quite a while before it really got into the mainstream. There will always be some visionary people who will introduce it, but the bulk of the people are laggard. So it takes a long time. So, for example, you can see all this work was done around 2000 and what 2006, and these plants have started getting put up around 2019. And also another thing that happens is that by that time people actually forgot who did what, and there's no memory. So people will go to places where people are good at doing publicity, and that's how people get lured and attracted. So many times, if you're a researcher, you can also get very frustrated, especially if you are inventing or doing something too far ahead. It's great in some ways doing it too far ahead, but it's only the visionary people, and their fraction usually is very small. The bulk of the people are effectively those who like to copy others. Once everything has been done, they also like to do it, and that's the majority, that whether we like it or not. So those are things that you must also remember, that timing is also very crucial in some of this. Now, another very good potential feedstock which has been talked about a lot is that you can also take algae which one grows, these are microalgae, and you can grow these, like for example in salt pans. You can put this microalgae, you can bring in seawater. These are salt tolerant algae, and then one puts in some nutrients, okay, and they start growing, and then after that you can harvest the mass. It looks like this, and then you can do a solvent extraction and take out oil. Now, this oil is just like a triglyceride oil. And in some ways, actually, this oil was found to be even superior in terms of the performance one got. Whatever process I showed you, this would be common to all. You can use it here, you can use it here, it doesn't matter. You'll use exactly the same process. The only difference may be that if, for example, sometimes oils have phospholipids, and phospholipids are very detrimental for performance. So the first step you might have to do is that one has to do what is known as degumming of oil, which is a standard process followed in the oil industry, where one removes the phospholipids, and then you can take the oil and they exactly follow this process. And so, whereas one advantage of the Jatropha oil is that there is no phospholipid in Jatropha oil. So that becomes a huge advantage of practicing this. The other is that once you get the biodiesel after this process, all of this stuff you can actually value add. So, for example, you can recover glycerol, you can recover fertilizer, you can make soap from the soap cake. So, not a gram goes waste. Everything is converted into useful products. In that sense, it is a very ideal process for rural areas, because rural area is also where you'll get your feedstock. They have to grow in agricultural fields or in some place like that. So putting up these plants in the vicinity of these agricultural fields would be the most ideal. And then these products, many of them are useful directly, like a soap, people require for bathing. So you can actually make use of every bit of it. Okay. Now, just to also tell you that unlike in the case of ethanol in some ways, after you're distilling it and you get pure ethanol, it's reasonably pure. It's just C2H5OH. Biodiesel is far more complex in the sense that, you see, I mean, as I told you, you may not actually do a full transesterification, and you may end up forming monoglycerides, diglycerides, some amount of triglyceride oil might remain in your biodiesel, some amount of free glycerol, which is generated, might remain there. You can have a problem with the oxidation stability, and you have to match a certain cetane number. So all of these are extremely important. And then why are we making the biodiesel? It is really to lower the viscosity. Regular vegetable oils are quite viscous, and as I told you, high-speed diesel engines cannot be operated with such viscous oils. So one has to reduce the viscosity, and the viscosity goes down by almost a factor of 7 or 8 when one does this transesterification. You have to go on and on, and you can see phosphorus content. Okay, there's a limit, 1 ppm. So what happens is that there are very stringent specifications which one has to comply with. Only after you have really been able to match all the specifications will it be roadworthy, especially if you want to use it as a 100% biodiesel. Another very interesting thing which you'll find quite amazing is that in the diesel engine, you can put it, as I told you, as a 100% biodiesel, but its flash point, and we'll later on discuss what is flash point. The flash point is very high, like normal diesel, which you get in the petrol pumps, will have a flash point about 55 degrees centigrade or thereabouts. This has a flash point of 160 degrees centigrade. And you would think that how can such a thing be a suitable fuel in a car? but that's exactly what it is. Because the diesel engine actually operates based on compression. You know that you apply compression, and that's how you raise the temperature to beyond the ignition temperature. And so if your cetane number is good, means that your which is over here, for example, it's ideal, almost very good cetane number. So what happens is that it allows for a very good compression of the fuel in the pistons, and therefore you can very easily reach the ignition temperatures, even though the flash point is extremely high. And the other thing is extremely interesting, that otherwise it has a very good safety margin. Like if you take a regular diesel, and if your car catches fire, the whole car can go up like this. But with biodiesel, if you use it in 100% form, then it's almost impossible for the car to catch fire. So you have a tremendous kind of a safety margin, and all of these properties are partly because of the composition of the oil that you take. That is very important. And so partly it is because of the nature of the oil, that is, how much of unsaturation do you have, because you need to have unsaturation, but not too much of it and not too less. Okay, and that is dictated by the iodine value. So you have to have the right iodine value. So all in all, you can see that it's quite complicated. Okay, there are many factors and parameters that you need to optimize while making your biodiesel. Let me also tell you that you see the trans esterification, the fatty acid methyl ester, which I showed you. What happens is that these biodiesels will tend to freeze if the temperature is too low. So if, for example, it's very difficult to go to a temperature less than -5 degree centigrade. You can do it with certain additives, like we work with Bama Lorry. They're very good in 4-point depressants. So one could reach about a -5 degree centigrade temperature. But suppose you want to say that I want to run a aeroplane with it. Now that becomes very difficult because at the altitude at which your plane is there, the temperature outside can be -40 to 50 degrees centigrade. And under those conditions, those biodiesels will completely freeze up. And so you cannot use those methyl esters directly for applications like in the aeroplane. Or if you take very cold countries, Canada, Russia, very cold countries, and there also you won't be able to use it neat because it will all freeze. So one will therefore need in certain situations to have a different kind of a biodiesel, not exactly the fatty acid methyl ester. Although frankly in our country there's no need for any of that, because most of our country doesn't get so cold, and so you can comfortably use it the way it is. You don't have to do anything. But if you're very keen that no, I want to run an aeroplane or something, then of course you need a different kind of biodiesel. So there what happens is that people actually try to take that triglyceride and literally only form the compound which is just like a hydrocarbon. So there is no oxygen or anything in that compound, which means that you need to be able to split it in places like these so that you can get rid of the oxygen, you can get rid of the glycerol, and that's what you have to do. And also those kinds of fuels will never have unsaturation. So you also need to make it saturated. And so you need to do some kind of a reductive cleavage of these triglycerides, and also you need reduction to eliminate these olefins. May not be completely, but for the most part. So that is what is done. And so you can do, for example, these would be the various steps. Like first you saturate, olefin saturation. So you saturate these. Then what you do is that you can have catalysts which just decarboxylates. So it just removes the carbon dioxide and I'll get RH. Or I can do a reductive cleavage where I'll get carbon monoxide coming out because I'm doing a reduction and I might be able to cleave it off that way. Or you can just do a decarbonylation. So the CO comes out as CO, I'll get an RH, and you have to add hydrogen so that H2 will take another oxygen and form water. So this would be like a reductive decarbonylation, and then you can convert this CO into syngas, and you can use it. You can also do hydro deoxygenation and completely reduce these to the alkane. So that's what you'll do. Now, you can imagine that these steps will require quite a bit of hydrogen. So now that is a complexity that you'll have to get hydrogen from somewhere. And obviously then you can see the process will get far more complex. You need hydrogen, you need high temperature, you need catalysts of a different kind. Whereas, what I showed you, the method of making methyl esters is very, very easy. Within 20-25 minutes, you can produce it. So those are the issues. But even then, the job is not done. Most of these fuels which remain liquid at temperatures like minus 40, minus 50 degrees centigrade are normally not straight chain hydrocarbons. Paraffin wax, it easily solidifies, but they are branched hydrocarbons. Branched hydrocarbons basically have their structure allows it to remain liquid. And you may want to go and read it up why that is the case. And in some cases, if your hydrocarbon chain length is too long, and I may not need it, I might want to make it shorter. What is required by, let's say, an aeroplane, whatever is the kind of chain length, you need to get that. So you may also have to do some kind of a reductive cracking. So that would be a cracking process. So these are the other steps. You can do decarboxylation, decarbonylation, hydrodeoxygenation, hydroisomerization, and hydrocracking. Now, these people were the first to actually do that in New Zealand. And around, I think, 2009, they ran a Boeing 747 following up on the work that was done in India. So they made an aviation fuel, and they could make a 50% blend with the kerosene type of fuel that is used in aeroplanes. And then much later in India also, one of the laboratories, Indian Institute of Petroleum, they were able to also make the same kind of fuel. And there was a trial run done from Dehradun to Delhi on that kind of a fuel. I think as a 20% blend, and this was a 50% blend, not with 100% neat biodiesel. Now with that, I come to the end of biodiesel. Now what we'll do is that we'll spend some time in talking about biocatalysis, okay? Because this is one of the areas which is really picking up a lot. Obviously, you can imagine that some of the chemical processes that we do, they are not really eco-friendly. So if you could do it as a bioprocess, it could be quite attractive. And it is not just for eco-friendly. That's only one of the reasons for carrying out a bioprocess. And in fact, that is one of the least reasons. There are other reasons for doing it. The most important is that bioprocesses typically tend to be more selective. That's extremely important. And let us look at what are the kinds of selectivity that we are talking about. The three broad types of selectivity are chemoselectivity, regioselectivity, and enantioselectivity. Chemoselectivity means if I've got a molecule where there is more than one type of functional group. Suppose I've got a OH, a CO, a CO2H, I've got a NH2, and let's say I want to only target one of these functional groups, and I don't want to touch the others. So that would be chemoselective, and there are many enzymes which do just that. They are tailored to attack one particular functional group, not all. So that's one. Second, even more demanding, you could have only one functional group, but it could be present in maybe two or three places in the molecule. Like if I've got a triamine, let's say with three amines in different parts of the molecule, and suppose I want to do some chemistry where I only want one of those amines to be targeted. That's another. The third, very important, is that as you know, most of our enzymes are chiral in nature, and it's because the amino acids and sugars, etc., we produce by all living organisms, they're typically chiral. You get chiral sugars, chiral amino acids, whatever enzymes, etc., you tend to produce, they tend to be chiral. And most of these also have excellent ability to differentiate between the two optical isomers of a molecule. And so they might only want to attack one and leave the other one behind. In fact, Louis Pasteur, one of the most famous work that he did was that he had left some ammonium tartrate sitting in a petri dish. It was a racemic ammonium tartrate. Uh, and then after a few days, he came back and he found that he had got a chiral material. Whatever was the bug, it had chewed up one of the enantiomers and it had left behind the other one. It didn't touch the other one. Those days, people used to think that only nature can give you chiral molecules. Nobody thought that you can also have human beings actually engaged in that kind of activity. Usually, I teach that in my innovations in chemical technology course in the final semester. Those are the things on which so many people have got Nobel Prizes, including the 2021 Nobel Prize has gone for this kind of asymmetric synthesis. Another reason is that most of the synthetic processes usually there's a lot of cooking involved. You need temperature, you need pressure, you may need a solvent, and so all of those become not so desirable. Whereas we know that nature, of course, must be operating under ambient conditions. If legumes are fixing nitrogen and making ammonia, they are not doing it at 200 bar pressure and they are, and 500 degrees centigrade temperature. They're just doing it at room temperature and 1 atmosphere pressure. So obviously there is a lot of attraction from that point of view, and from the green chemistry point of view. Many times, when you're making a very complex pharmaceutical product, which might involve maybe 10, 15, 20 steps, and you might find that that your overall yield may be just about 5 to 7%, and all the rest of it is waste. So you can have a tremendous environmental burden from all kinds of waste that are generated in the course of these synthetic protocols. So those would be the reasons why one would want to do a bioprocess. I have taken this presentation by this company called Innocin. It's a beautiful presentation. So most of these are done with some kind of enzyme. Some things are done with the whole cells. You don't have to isolate enzymes. But in many cases, you isolate the enzymes and then you carry out the further reactions with those enzymes. Enzymes are also a tricky thing. Like most of them are done through microbial fermentation, and there are specific bugs which produce specific enzymes. But it's not just microorganisms. You can also have animals which can produce some very useful enzymes. You can have the latex, the plant latex has enzymes and other bioactive things which you can make use of. Now, what happens is that if you are doing a microbial fermentation, there are two situations that can arise. Okay? One is that the enzyme which is obtained is actually released by the organism into your solution medium, in which case it will be there in the solution, and all I have to do is I just need to filter, and I've got my enzyme in my solution. and then I can concentrate it and do other things with it. And that's fairly simple. Like, for example, when one is making ethanol and the yeast, obviously the kinds of enzymes they are producing, those are actually released into the solution. It's not happening inside the cell. But then there are others where the enzyme accumulates within the cell and is not released into the solution. In which case, I have to take it after the growth of the microbes, which we had talked about last time, the lag phase, log phase, and all that. And then you have to disintegrate the cell. And after that, you may need to do a solvent extraction. And because you have disintegrated the cell, things like nucleic acids, etc., will also get in along with your enzyme. So there has to be a purification process. So it gets more complicated if it is a intracellular production of enzyme and which is not getting released. The second is that most people don't use the enzymes directly in solution state. It's been found that if one immobilizes the enzymes, the stability tends to improve. So there is a huge amount of work which is done on immobilization of enzymes. Now, you as chemical engineers will, of course, appreciate the value of immobilization. Like, for example, if I immobilize and I make a enzyme bed equivalent to your catalytic bed, and imagine that I am passing my raw material from here and it's reacting, the enzyme is taking care of it and I'm getting my product over here. What could be better? That's the best if I can do it. Another is that obviously the recovery becomes much simpler, whereas if I've got enzyme in my solution and I'm getting product in solution, naturally I have to again separate out that enzyme again from the product. So it becomes another complication. And the third is most important, that it has been found that immobilized enzymes typically have better stability. They have a better shelf life and you can keep them stable. So that is one of the most important reasons for doing immobilization. Now, there are two common processes which are followed. One is that most of these enzymes have a surface charge. So once I know what is the nature of the surface charge, is it positive or negative, now I can create some kind of, let's say, a network, a polymer of some kind, which is also a charged polymer and maybe having the opposite charge to whatever surface charge you have in the enzyme. So for that, you need to know the zeta potential, all of those instrumental techniques you need to have so that you can determine the charges. And then these are really held together by electrostatic interactions. That's it. They're not very strong interactions. Or in some cases, you might even induce a hydrogen bond. There could be a very strong hydrogen bond between your enzyme and the matrix. There's a second way to do it, that you have your enzymes in solution, but what you do is that you create a gel in situ in the solution, and the gel will form some kind of a network like this, and the enzyme will get trapped inside the network. So it's a very porous network, but it is still, the pores are not big enough that the enzyme can come out. But the pores so big that there is no problem in your starting materials, anything that you are doing a enzymatic process on, those will freely flow in and out. There's no problem. It's just that the enzyme will not come out. So it's something like a tea bag. Like I have a tea bag with my tea inside, and when I put boiling water outside, the water goes in and leaches out only the desirable constituents from the tea, and not the leaves. The leaves are left behind in the bag. So much the same kind of a concept in this kind of a trapped immobilized structure. Let us also look at a couple of other things, that when one is doing biocatalysis, there is a lot of room for creativity. I mean, like A to Z, let's say I'm doing it synthetically, and I again start with A and I produce Z by a bio process. It may not be, it could be though, that I am circumventing these steps, B, C, and maybe I'm introducing a new step where I produce a intermediate Y. I don't produce B or C, and Y gives me Z. So if, for example, if you are too adamant that no, I just want B, tell me how to have a bioprocess for B, you actually may not be doing the most wise thing. The wisest is to say, I need Z. Let's not worry about how I'll make Z. If it means a different intermediate, so be it. I don't mind it. Or you can even change the feedstock completely. I might find that no, instead of going from A, if I take X, and I might find it easier to go to Y and Z. It need not even be Y. It could be some other thing that I form and go to Z, or from X I might go straight to Z, and it might be easier to do. So you need that kind of imagination. Your focus should be what is the cheapest raw material that I'm using, or what is the raw material that is available to me. That's very important. What is the shortest route to take? And where am I conserving my resources maximum? That's it. I mean, as chemical engineers, those are the kinds of questions you should ask. You should not be excessively concerned about B and C and things like that. I want to reach Z, and I want to know the best way of reaching Z. So let's look at some examples of biocatalytic route. These are all processes which are the best commercial processes. So let me take you, like for example, this is a drug, Pregabalin. It's an anti-epilepsy drug. It also helps to soothe the nerves. This is the molecule, Pregabalin. Now you can see that in this molecule, this is a chiral center, and this is the chiral form which is preferred. Now remember that in many of these drugs, sometimes the opposite enantiomer is not only not active, but it can even be harmful. That's why everybody wants to make these kinds of drugs in a very, very selective manner. And so you don't want that other isomer to be there. So let's look at, for example, let's say this particular raw material is available. It's quite straightforward to produce. So they start with this. Now, what they do is that they found a lipase. Lipase acts on the ester groups. Now, what this lipase does is that it hydrolyzes one of the esters. There are two over here. It hydrolyzes one. Secondly, the lipase only acts on one of the isomers. This is a chiral center, right? There are four dissimilar groups. What that lipase does is that it only touches when the cyano is in this disposition, only that enantiomer it hydrolyzes to CO2 Na plus, CO2 minus Na plus, and doesn't touch this. Now, because I formed a sodium salt, I can actually just take it into water. So I've just taken it into water. I've got a pure optical isomer now. And what they do with this is that, they've developed a method by which this chiral, the wrong isomer, can be re-equilibrated. And so again, from the wrong isomer, I can generate the racemic. So every time I go through this process, I will again, that part of the racemic, which is in this form, will get attacked. And that way, by continuously recycling, I can effectively convert all of this into the desired molecule. After that, all they do is, this is what I want. This is simple. I just have to do a hydrogenation of the cyano group, and I'll end up getting CH2NH2. That's what this is. And I have now made this compound in my required chirally pure form. There are many options. This is not the only option. Okay. Like for example, there is another lipase which doesn't do the job with the cyano, but it does it with the nitro group. So I have a nitro group, otherwise it's doing the same thing. It is only attacking one, and then I can reduce the nitro to amino. So I can again produce the compound from a different raw material. Someone might say, I have this raw material. Another person might say, no, I have got better access to this raw material. So you can decide. I'm not going to go through all of the approaches, but over here, they have shown 4 different approaches where I can actually carry out this kind of selective thing. Now, there is also an element of luck because you see, it so happens that this particular lipase gave me the right isomer because I've got this. If it had, for example, attacked this, it would have been no use. And there's a huge amount of trial and error which goes into this kind of biocatalysis. And along with it, there's a lot of genetic engineering. People are constantly doing genetic engineering to try and tailor make these enzymes just so that they can improve their specificity. Take another case, let's say where you can, aspartame, you would have heard of aspartame, it's the sweetening agent. This is the compound, this is your aspartame. Most important is really to be able to produce this compound. And this compound is produced with this NH group having a protecting group, which otherwise interferes with the process. And after this molecule has been assembled, then I just do a deep protection. That's all. So it's basically forming a NH2. Now, what happens is that, let's say, they found that, for example, this particular molecule and this particular molecule, if I react, I can get this. This you can see, this is this part, the aromatic ring, this is your this group, the same group, and you've got an NH2 over here. And that NH2 then has to react with an acid and it has to form an amide group. That is their amide group over here, this group, okay, NHCO. It is formed from the reaction of an acid with the say primary amine, NH2. Now, the first and foremost thing to look at is that I have got a situation where this molecule, you can see that the NH2 group is in one disposition. This is a chiral center. First is that to remember that this molecule over here can exist as 2 isomers, this one and this one. Now, out of that, only this one I need, because this one will give me the wrong product, because I'll get the wrong isomer starting with this. I will get it exactly the opposite isomer if I do this. So first, it has to, whatever is the enzyme, must be able to first and foremost only utilize this, not this. Second, I've got 2 options. You know, I can make an amide over here because there's also a carboxylic acid, or I can make an amide with this carboxylic acid and this amine. Now, this is the one, you can work it out, which will give me my desired product. This is the one, not this one. So what happens is that this particular enzyme, thermolysin, does all of that. It basically only allows the reaction with this enantiomer. Secondly, it does the regiochemistry perfectly, and it only reacts with this carboxylic acid. This is green, and these are all wrong. It's not going to help me. So that's what it does. And it basically ends up producing this molecule, and then I just deprotect it and I form my desired product, aspartame. So you can see that this is done at kilotons level by this company DSM, the Dutch company. That's the kind of brilliance which you have. And the second thing that they're doing is, because an enzyme is usually a fairly big molecule, they also will do an ultrafiltration, and so that these compounds are much smaller in size, so they will permeate through, and my enzyme will be held back. So I can then again recycle my enzyme, the thermolysin. So this is another example where you can see how both enantioselectivity as well as regioselectivity have both been put together in this particular bioprocess. Take another case, and this is a very, very important antibiotic, Cephalexin. It's a beta-lactam. It's a very broad spectrum antibiotic, which is used to treat a variety of bacterial infections. Now, beta-lactams are also very, very delicate because it has a four-membered lactam. This is a lactam group, and it's four-membered. Anything, if you try to do synthetically, it's very tricky to do it. Now, first and foremost, they found a particular enzyme which is obtained from the penicillium and which basically takes sugar as the substrate, and it makes this particular molecule. And this particular molecule is known as penicillin G. Now, after that, what they were doing was that they need to make the cephalexin. So, what they have to do is that first they need to hydrolyze and remove this part so that I'm left with the NH2 group here. That's the first thing. Very, very difficult to do, delicate stuff. Second, this is a five-membered ring, this nitrogen sulfur heterocyclic compound, and whereas this is a six-membered ring. So they need to do a ring expansion. From a five-membered ring, they need to do a expansion of the ring chemically to six-membered. Once they have done this, then of course this NH2 group and this COCl you can react, and then you'll form the amide, and you can put in this group. Here again, there's a lot of trick. You cannot just do it in a straight manner. Some of these functional groups will need to be protected, like this particular group. You can see it is protected, PROT. So it's protected, and later on, this functional group is again deprotected, and I convert it into a carboxylic acid group. So this carboxylic acid group has to be protected when you are reacting this NH2 with the COCl, this acid chloride. Now, overall, this particular process, I think it takes about 13 steps. And you can imagine, when if you get 90% conversion in each of the steps, by the time you carry out 13 steps, how much product will you get? You'll barely get less than 10%. Now, what they did was they were able to do a genetic engineering of this particular penicillium, and it has a remarkable property. This particular thing not only gives you this part is the same as you can see, but remarkably, it also expands the ring. So you don't get this, you straight away get the six-membered ring. And then you can imagine, I mean, how simple it is. After that, of course, they have to use another enzyme, gluteryl acylase, and where they are basically cleaving the amide and being left with the free amine. And then, of course, I reacted with this stuff, and I can end up forming this. So there's a massive simplification of the steps just by doing a bioprocess. So obviously, nobody is going back to a chemical synthesis because it cannot compete. I mean, I'm not even talking about the environmental cost in terms of all the side products, this, that, the time involved. I'm just talking about plain selectivity. It's almost impossible, to compete with this kind of a process. You would have got another example, and this is a semi-synthetic approach, because one is that I'm doing it naturally, the fermentation up to this point, and then I'm doing it synthetically. Like over here, I'm doing the acid chloride reaction synthetically. Take another, I think this is the last example, just to also show you that everything doesn't necessarily come from a microorganism. Like the rubber plant, actually the sap which you get, you can see the latex. This particular latex contains a particular yeast. This is the yeast, and it produces an enzyme. That enzyme has got a remarkable property that it can induce cyanohydration. In other words, I'm adding an HCN across this aldehyde group over here. This is a prochiral center. You see, like when I put the HCN group, then this carbon becomes chiral because I've got 4 different groups here. So what happens is that this particular, what is called as hydroxynitrile lyase, this stuff is HNl, is able to do the hydrocyanation in a very chirally selective way. And it gives you only this particular form. It doesn't give you the other form. Why was this so important? Because there is a pesticide, and this is one of the hottest selling pesticides. These are known as synthetic pyrethroids. Pyrethroids typically have a 3-membered cyclopropane ring, and these are some of the most versatile pesticides that are available, used world over. This is the structure. So someone would have realized that, look, if I can break up the molecule such that if I can have a OH group, like if I hydrolyze this part so that I have maybe a ester form or a CO2H, and over here if I have an OH, and then later on I do a esterification, I can make this molecule. So what do I need? They have processes for making this part. This part is fairly standard. But this part was hugely complicated to make it in an optically pure form. So by using this plant-based lyase, this stuff, they are able to actually get this part. And all I now need to do is hook it up with the carboxylic acid of this particular compound, and I've got my product. So these synthetic pyrethroids have been produced by this kind of a process, and enormous simplification of the entire synthetic protocol. So I hope you have been able to appreciate the different kinds of bioprocesses, and this is one of the hottest areas. In fact, just yesterday, one of the students who passed out last year, chemical engineers, Abhishek Bhardwaj, he sent me a mail talking about this course, and then he mentioned that he's just about to start work in a biotech company, which is involved in genetic engineering. A lot of the people who are going abroad also to do their studies, many of them are shifting over from mainstream chemical engineering to actually biotech companies. Many of them are doing their PhDs in the biotech area. Chemical engineers have a huge role to play in all these bioprocesses, and I'm not surprised that so many chemical engineers are now shifting to this biotech area. Of course, these are all done by interdisciplinary team of researchers. It's not done by one person. Let us look at some of the challenges and key success factors for biocatalytic production. And I've deliberately put this slide because it is relevant to the chemical engineer. One is that this whole process of being able to produce the biocatalyst by a fermentation process with the lowest cost, because if it is very costly, then people will not be able to use it. So it has to be highly cost effective, and that's something chemical engineers are very good at, process optimization and making it practical, and also improving the rates of the reactions by better understanding of triggers. What are the things that actually promote the rate? Biocatalytic reaction engineering, that's very, very important. Like I showed you here, this is all part of biocatalytic reaction engineering. How exactly are you going to do the process? What should be the catalyst load? What should be the batch cycle time? All of these are so important. The enzyme engineering is, of course, as I told you, done by genetic engineers. Immobilization and recycling, another very, very critical step. And to integrate all of these various things that one needs to do individually to make the process successful. So with this, I come to the end of two things. One is, as I told you, the bioresources, how to utilize bioresources, and increasingly, I think that there should be a greater and greater emphasis in generating more and more bioresources. The second is subsequently doing bioprocesses, not just making ethanol and biodiesel, but making the most sophisticated organic molecules, which play a profound role in things like pharmaceuticals. Now, of course, because of COVID, you know that how important vaccines are, and these have all got to be synthesized for billions of people. So you can imagine the kind of technologies that one needs to develop. And in fact, just 2 days back, someone sent me a mail. I was surprised. This person, he said that one of the most critical steps in the bioprocess is actually doing large-scale chromatography. So you might have thought that chromatography is an analytical tool, mainly used to identify what exactly you have formed. But that's not true. That chromatographic separation is actually now being used even in a process. And he said that their company specializes in large-scale chromatography.